Let's examine another statement related to climate change. There is no way to reasonably determine whether any observed climate change is because of human activity. True or false? False. There's no logical fallacy here. This statement is just factually wrong. We have several ways to demonstrate that climate change is influenced by and attributed to human activity. To argue otherwise ignores a wealth of data collected from scientists from around the world. Let's go through a few lines of evidence. If we look into the past, we can see a strong correlation between temperature and atmospheric carbon dioxide concentration. Here's a graph of temperatures from 1880 to 2020 that we've seen before. Remember how the blue bars show temperatures starting off cool, and the red bars show temperatures becoming warmer than the 20th century average, and then getting warmer and warmer and warmer. The gray line that's been added to this chart is the carbon dioxide concentration in the atmosphere. Look at how the pattern of concentration matches that of temperature. And it's not just pattern matching. Understanding how the atmospheric physics works through the greenhouse effect provides a mechanism for the correlation. More greenhouse gases interacting with outgoing radiation, more heat being trapped in the atmosphere. It works if we go further back in time, too. Here are 2,000 years of data for carbon dioxide. The blue dots are measurements of carbon dioxide in ice cores in Antarctica. Scientists extract the gas from tiny bubbles of air trapped since the glaciers froze. The red dots are direct measurements of carbon dioxide in the atmosphere in Tasmania. You can see how the ice core data line up really well with the direct measurements. Also note that the carbon dioxide concentrations were very stable from the year zero all the way up to about 1800, when the Industrial Revolution really began to add greenhouse gases to the atmosphere. Now, let's add temperature. First, the big picture. Just like carbon dioxide, temperatures were fairly stable from year zero to sometime in the 1800s. Sure, there was some interannual climate variability and some prolonged warm and cool periods, but really pretty stable, pretty flat black line until the late 19th century, when it begins to rise quickly, just like the carbon dioxide does. Okay, now let's add some detail. How do we know temperatures before there were good thermometers? We can use things called proxy records. These are things like tree rings, corals, and sediments, where we understand how they relate to temperature in the modern period and why they behave that way. Understanding those relationships lets us measure things like the growth rings on trees and coral and use them to calculate what temperatures were hundreds and thousands of years ago. The gray band along the black line in the temperature graph represents our uncertainty in temperature estimates associated with using the proxy records. But you can see that even with uncertainty, modern temperatures are definitely higher than they were for the last 2,000 years. And we can go even further back in time using ice cores. This record takes us back 800,000 years. We see that carbon dioxide concentrations in bright blue go up and down between about 180 and 280 parts per million. And with every change in carbon dioxide, there is a corresponding change in temperature, shown in light blue. The temperature ranges are things that go from pretty similar to what they were in 1800 to up to 9 degrees Celsius colder. Those are the ice ages. We were already in a warm interglacial period before the Industrial Revolution. Now, atmospheric concentrations of carbon dioxide are much, much higher. Currently, November 2022, we are about 418 parts per million, and we go up about 3 parts per million every year. So where is all that carbon dioxide coming from? We've already talked about how greenhouse gases trap radiation in the atmosphere, converting it to heat. We've talked about how the concentrations of greenhouse gases have been increasing over time. Let's dig a little deeper now and talk about where those greenhouse gases are coming from. Here's a pie chart showing the global emission by economic sector in 2010. Okay, it's 10 years old, but things really haven't changed a lot since then. The biggest source of greenhouse gas emissions is fossil fuel combustion. we see fossil fuels show up in several places on the graph. Fossil fuels are used to produce electricity and heat, which contributes to 25% of global emissions. The industrial combustion of fossil fuels in factories is a big piece of the 21% of emissions that come from industry. Transportation by road, rail, air, and ship is another big piece that comes from fossil fuel. 95% of the world's transportation energy comes from oil and gas. There's a slice of pie for buildings, and this relates to burning fuels on site in the building for heat or for cooking. Think gas stoves and water heaters. And then there's the other energy slice of pie. This is all of the emissions that we release associated with getting fossil fuels ready for combustion. This is the process of fuel extraction, refining, processing, and transportation. So, what isn't fossil fuels on this graph? Mostly, it's the 24% that's agriculture, crops and livestock, and deforestation. And the graph doesn't account for the work that ecosystems do to remove carbon dioxide from the atmosphere in plants and soils. That carbon removal offsets about 20% of the agricultural emissions. In addition to doing inventories of greenhouse gas emissions by country and economic sector, we have another way of knowing that greenhouse gases in the atmosphere are coming from fossil fuels. That's by looking at the weight, or isotopes, in the carbon atoms themselves. Plants like light carbon atoms, and they take that lightweight carbon out of the atmosphere preferentially. Then, when we burn the plants, we add that lightweight carbon back into the atmosphere. This is true whether we are burning modern plants, like forest fires, or fossil plants, like in coal or the phytoplankton that forms oil and gas. So, the lighter the mass of carbon atoms in the atmosphere, the more we are seeing the effects of fossil fuel combustion. This is measured in an area with super clean air, Tasmania in Australia, and we can see that the signal of less heavy and more light and plant-like carbon over a period of several decades. So we know that greenhouse gases are getting into the atmosphere from human activity, mostly fossil fuel combustion. And we've already learned that greenhouse gases interact with energy given off by the Earth to trap heat in the atmosphere. Now let's put them together to see how they contribute to the warming that we are experiencing with modern climate change. This graph shows that there has been about 1 degree Celsius of warming so far, relative to a baseline of 1850 to 1900 average temperatures. We can use climate models, which we'll talk about later, to figure out or attribute the cause of that warming. If we look at the influence of all our greenhouse gas emissions combined, we see that they would create about 1.5 degrees Celsius of warming. The only reason we haven't warmed that much is because of other things that humans are doing, mostly adding air pollution, that's keeping the warming down to only about 1 degree Celsius so far. And the natural variability of Earth's climate, solar activity, and volcanoes over the past 150 years haven't really caused any warming at all. We can also go one step further and break it down by the type of gas. We can do this from the physics of how the different gases absorb energy and their concentrations in the atmosphere. Here we see that most warming can be attributed to carbon dioxide, followed by methane. And in terms of the air pollution, keeping things a bit cooler in the atmosphere, that's mostly sulfur dioxide, largely associated with burning coal. It cools the atmosphere through tiny particles and droplets called aerosols, which scatter the incoming solar energy. Of course, the cooling effects of sulfur dioxide from coal combustion don't outweigh the warming effects associated with the carbon dioxide emissions it generates and all of the other environmental effects like acid rain. Okay, so let's summarize what we know about the links between climate change and human activity. Carbon dioxide is a greenhouse gas. As concentrations increase, so does temperature. We see that on timescales ranging from 1 century to hundreds of thousands of years and even further. Carbon dioxide increased in the atmosphere following the Industrial Revolution, which is when we started burning fossil fuels on a large scale. The chemical or isotopic signature of carbon in the atmosphere looks like it comes from fossil fuels. And computer models cannot reproduce climate without accounting for human activities.